Okay, we're now on part two. I'm going to have a brief introduction into the mechanics behind the changes in the sky, so we can see why a site pointing northeast is oriented on the midsummer sunrise, and why matters become a lot more complicated when we start to look at stars. So you have to forgive me with this because I'm not a scientist. But first thing to explain is that the Earth sits on the same flat plane as the rest of the planets orbiting the Sun. I mean, there's slight variations in the plane, but this plane is called the ecliptic. There we go. There's the Earth there, and it's going around the Sun like so. Again, forgive my shaky hand. But it's going around the Sun like so, obviously once every year, and then turning on its axis once every 24 hours, which gives us a sunrise and sunset. But the reason the Sun doesn't just maintain a flat point in the heavens and it rises and sets in a curve is because the Earth's axis isn't completely flat, isn't completely north, isn't up in relation to the ecliptic. Exactly, there's a 23-degree tilt of the Earth's axis, which means that we don't see the planets and Sun passing us in a straight line, but at an angle. That's the angle that the Earth is at. You know, we're tilted at a certain angle, so it seems that the rest of the Sun and planets are at this slight angle, rising and setting because the Earth is tilting on its axis daily. You all know this anyway, but what it does, it gives us the daily undulation of the Sun rising and setting. Now, this pattern is obviously a daily pattern, but there are variances in the height that the Sun reaches in the sky and the rising and setting points of the Sun based on our position relative to the Sun throughout the year. So because the Earth is pointing at this 23-degree angle from the ecliptic, when we're in a certain position in this yearly cycle, we're pointing towards the Sun, and when we're in another position, we're pointing away from the Sun, and that gives us summer and winter. Here we are. So at the summer solstice, us in the north, because of the 23-degree tilt of the Earth's axis towards, sort of away from upright, we're then pointing towards the Sun. So we get more sunlight, basically, that time of year. At the equinoxes, the tilt doesn't really affect the issue at all. So we have equal days and equal nights, but then when we get to the winter, we see that the northern hemisphere is tilted away from the Sun, and so therefore the Sun is lower in the sky and the days are shorter. Now, this diagram here on the left shows this variance, this kind of metronomic swing from longer days to shorter days. So at the equinox, the Sun is rising due east exactly. This is both in the spring and the autumn, but in midsummer, the Sun is rising in the northeast, and in midwinter is rising in the southeast. Now, this diagram doesn't make it look like there's quite a bit of variance, but there is. Now, look at these images here. This is a reconstruction from Stellarium, the program I'll talk about later, showing the relative rising and setting points of the Sun throughout the year. So this is midsummer, 21st of June, and we can see the Sun is rising in the the northeast over here. Go to the equinoxes and we can see the Sun rising in the east here, behind this tree, and we go to midwinter, and we see the sun is right down here, right down in the southeast. So that's a massive difference. I mean, it's a large portion of the sky. So obviously we can see if an entrance to a site is aligned this way or aligned that way, there's quite a bit of difference. It also affects here again we have the tilt in the Earth's axis. It affects the height that the sun reaches in the sky. Now, it's not overly important, this, in terms of archaeoastronomy, because archaeological sites that are astronomically aligned tend to fixate on the horizon, on the rising and setting points, rather than the height that the sun reaches in the sky. So I'm just putting this in for interest's sake, but it's not really important in terms of archaeoastronomy. So midsummer, the sun is at its highest point because it's obviously rising in the northeast. We have the equinox, it reaches kind of midpoint of the sky at midwinter. I mean, it's barely kind of scraping above the horizon there. But again, it's not overly important when we're looking at archaeological sites, which the height in the skies, and we're looking at positions on the horizon. That's the important point for us. Now that's the sun. As I said, the sun and the moon don't overly change their positions. I'm not going to go into it too much today, but the moon has its own cycle, which is a 19-year cycle called the Metonic cycle. But the rising and setting points tend to be within that kind of butterfly shape that I showed, and that it hardly alters over time, maybe by a couple of degrees. But within the time period that we're talking about, going back to 4000 BC, it's not any variation in the rising and setting points at the solstice and equinox is hardly to be factored in. It's not important. But as I said, this is not true of the stars. The stars change position due to something called precession. Now, the precessional cycle is due to this slight wobble of the Earth's axis. As I said, the Earth's axis is at 23 degrees, and it's pointing to obviously the north in the heavens at the pole. But due to this slight wobble, which is something to do with the position of the moon, I won't go into it. It's not really important why it happens, only that it happens. It means that the Earth is spinning like a top, like this, but there's a small variation in the rotation of the Earth's axis, which means that the stars that it points at, true north, alter over time. It in fact describes a circle in the heavens, and it takes 25,920 years to describe that full circle. This is called the precession, cycle of precession. I'll explain why in a second. But what it means is that the background stars are slowly shifting over time. Now, the way to explain it was called the precession of the equinoxes when it was discovered in ancient Greece, sort of, I think it was about 200 BC by someone called Hipparchus. And he noticed that the constellations against which the sun rose at the equinoxes, let's say the spring equinox, gradually changed over time. And when I say gradually, I mean very gradually. I mean, it's 72 years for 1 degree of change. So in your whole lifetime, the background stars would only change by 1 degree. And then the whole cycle, as I said, would take, let's say, 26,000 years. To try and explain it a bit better, as I say, the background constellation against which the sun rises at the equinox changes. Now we're currently in what is known as the zodiacal age of Pisces, but we're on the cusp of the age of Aquarius, hence the song, the dawning of the age of Aquarius. Now this means that the sun at the moment, on the spring equinox, when it rises, the constellation of Pisces, we're on the cusp of Pisces and Aquarius, that's the rising point of the sun. Now, 2,000 years ago, obviously there had been a longer shift over time, 72 years for 1 degree. It meant that the sun was rising at the kind of start of the constellation of Pisces. People have commented that this is the age of the fish, and it's to do with Christ as fish and fisher of men, all this kind of symbolism. 2,000 years before that, the sun was rising against the background constellation of Aries in the spring, and this was the season of the ram, when you had ram-headed gods in Egypt, and you had the sheep and ram symbolism in the Bible. 2,000 years before that, you're getting towards the age of Taurus, and you see a lot of bull symbolism. Well, whether this is how accurate this is, Carl Jung wrote a lot of information about this, about the different zodiacal ages. Anyway, what it's showing is that the background stars change over time, and so as an archaeoastronomer, you need to know. When you're looking at a site and the site is pointing like, I don't know, 50 degrees east, it's not enough to know what stars are there now. You have to know the age of the site in order to reconstruct what stars were in that position at that time. And it can actually help the other way if you know roughly sort of what stars were used in a certain culture's mythology. You could look at a temple, say, that's oriented towards those stars, and then you can date the temple using the same sort of archaeoastronomy programs, which I'll talk about in a bit. I don't want to labour this point too much, and I already have, I think. But here's a simplified diagram showing, due to precession, the sun's address at the spring equinox, known as the vernal point, changes its zodiacal sign every 20,160 years. And we also see this shifting of the stars also affects the height of certain constellations over time. And certain constellations which were visible in the past are no longer visible, but they will be again due to the cycle of precession. This is showing the relative positions of the constellation of Orion. So at the moment, Orion is very high in the sky. And when the pyramids were built in about 2,500 BC, Orion was kind of at a midpoint in its cycle, and this is when the star shafts of the Great Pyramid point towards the belt stars of Orion. But Orion, at its lowest point, was not too far above the horizon. Now, at this time in Britain, this is about sort of 10,500 BC, when it's at its lowest point, you couldn't see Orion in Britain. So I think I've got some images of that coming up. Yeah, this is Orion at its high point. This is now. So looking at the night sky now in the winter, you will see Orion at its highest position, quite high in the sky. And you go back to the age of Stonehenge, and Orion is a lot lower in the sky. You go back to, let's say, 6,500 BC, and the belt stars of Orion never appear above the horizon. Go back to 10,000 BC, and you're not going to see anything below this kind of line. So this limits, when we're looking at explaining what sites, what stars ancient sites were aligned on, there are limits. Certain constellations which are visible now weren't visible then. And this is something that we can only only sort of discovered through the use of this astronomical software. So that's why a lot of archaeoastronomy hadn't taken place in the past. A, because we didn't know the proper age of the sites, and radiocarbon dating has helped us with that. And B, because we didn't have the computer power to reconstruct the ancient sky. Now we have both of those techniques. We can really start to use them to try and work out if there were astronomical alignments, when they took place, and what was being looked at. Okay. And as I said before, this can then lead us on. If we know what stars are being looked at, we can start to try and fathom what the stars may have represented, and try and reconstruct belief systems and rituals